All right, it's 11:30, about 15 minutes left in class. I'm going to begin working through this practice problem that you see on the projector here. It says a solid cylinder is lifted out of oil by a wire attached to a motor. Figure 5.1 shows two different positions, X and Y, of the cylinder during the lifting process. The motor is fixed to an overhead beam. The cylinder has cross-sectional area 0.018 meters squared, length 1.2 meters, and weight 560 newtons. The density of the oil is 940 kilograms per cubic meter. It says throughout the lifting process, the cylinder moves vertically upwards with a constant velocity of 0.020 meters per second, and the viscous force of the oil acting on the cylinder is negligible. The first thing it asks us to do here is calculate the density of the cylinder. Let me see if I can use my tool here. All right, so we want the density of the cylinder. So let's think how we could approach that. Density equals mass per volume. We're given not the mass, but the weight of the cylinder. And so remember that weight is equal to mass times the acceleration due to gravity. And so think about how you could easily calculate the mass of that cylinder by just dividing 560 by 9.81. Right, so we know that the mass here is 57.08. We'll even say it's 57.1 kilograms. Any questions where that came from? The volume of a cylinder is the two-dimensional area of a circle, okay, and that's actually given. That's cross-sectional area, 0.018, times the third dimension, length in this case, right? So area times length, 2D area times the third dimension gives us a 3D space it takes up, the volume. And so it's this number in square meters times this number in meters would give us a volume in meters cubed. Right, those are good units for volume, so just multiply 1.2 by 0.01. So 0.018 times 1.2 means the volume of that cylinder in cubic meters is 0.0216. So take that ratio of mass to volume, that's what density is. 57.1 kilograms divided by 0.0216 meters cubed gives us a density rho equal to, the calculator value is 2,643. So 3 significant digits, let's say 26. Kilograms per cubic meter. I'm recording this, and so if you didn't get all these notes down, just take a look on YouTube later and pause the video. Take all the time in the world with it. In the interest of our class time here, I'm going to move it right along. The question goes on to read, for the cylinder at position X, show that the upthrust due to the oil is 200 newtons. Let's remind ourselves, as we were at the beginning of class, remembering that there are different types of forces affecting the motion of an object. Upthrust is a force that is the result of collisions of sort of particles here. And so there are more collisions between the particles in the oil on the bottom surface of it than there is, say, on the top here, because as we get deeper and deeper down in the fluid, remember that the pressure there increases. The pressure is force per area. So this explains, the upthrust is sort of the force that explains why things float, why a hot air balloon rises. Okay, there are more collisions on the underneath side of it than there are above it, so there's a net force acting upwards, and so that's why we call that force upthrust. How could we determine that the upthrust here due to the oil is 200 newtons? All right, so that's what we're trying to do. Let's consider the cylinder in the oil. And remember that the cylinder has a height of 1.2 meters. I'm calling it a height, they called it a length. But remember, we're looking at the idea here that pressure in a fluid is equal to the density times the acceleration due to gravity times the height. So it's this delta H that accounts for the upthrust here, that there is a difference in pressure from the top side of it here to the bottom because 1.2 meters lower, the pressure is higher. So there are more collisions between the oil particles sort of crashing into the wall here and then bouncing off than there are up here, and that means there's going to be a net force acting up. And so the pressure there is equal to, they gave us the density of the oil, 940 kilograms per cubic meter. Acceleration due to gravity here on Earth, 9.81 newtons per kilogram. And then the height is 1.2 meters. And so this would give us the pressure right here compared to, the difference in pressure, I should say, between here and here. There's still atmospheric pressure up here, but there's more pressure due to the oil down here, and that's going to create a net force there. If we're trying to calculate the force is 200 newtons here from the upthrust of the oil, then let's remind ourselves that force is going to be pressure times area, because pressure is force per area. And so we can use this equation to calculate the pressure. And we were given the area of this cylinder right here, right? So this is just going to be the product of 940 kilograms per cubic meter, the given density of the oil, 9.81 newtons per kilogram here on Earth, 1.2 meters, means there's a change in pressure from the top of that container to the bottom right here at the bottom of the cylinder. The pressure is 11,065 pascals, which are newtons per meter squared. We were given the area as 0.018 meters squared. And so that should solve for the force, again, due to the collisions of all these oil molecules crashing into the surface, changing their direction. So we saw the other day how it's a very general sort of idea of an object crashing into a surface perpendicular and then bouncing off. There is a force, there is a change in momentum, 2mv. And so if you multiply these two things, it should give you something close to 200. The question goes on to ask, calculate for the moving cylinder at position X the tension in the wire. It's only a 1-mark question, and so we might expect that shouldn't be too difficult of a calculation. We really just do have to make sense of the concepts in order to make short work of this calculation. So the wire is pulling up on this cylinder, but it's saying at position X. Well, that's when it's sort of submerged in the oil. So we were given the weight of the cylinder, 540 newtons, I think. It was 540 newtons. That was the weight of the cylinder. But remember, there's an upthrust force. So weight acts down, the upthrust acts up, right? And so there was a 200 Newton upthrust force that's sort of pushing it back up, right? And so the tension in the wire has to provide all the rest of the force to lift it. In other words, it's getting some help from the upthrust force pushing it up. The wire's got to pull the rest of that weight. And so it only has to provide 340 newtons of force to lift a 540 Newton weight if there's already 200 newtons of upthrust. Now note what's going to happen as we begin to lift it. We're no longer going to have that much upthrust. Remember, this is a result of it being that low in the oil, right? At that depth, 1.2 meters down. As we lift it up, there's going to be less and less upthrust, right? Eventually the tension is going to have to supply all of the force to lift the weight. The power output of the motor. So at that position X, when it still is, submerged all the way, what's the power output? Well, you may recall that power is force times velocity. So this is the force that the motor has to provide, right? Sort of providing the tension in the string. The velocity was given at 0.02 meters per second. And so we could solve this by just considering There was a force of 340 newtons. The velocity was 0.02 meters per second. My bad. Look at that, you guys. 560 newtons. $560 newtons of weight minus the 200 newtons of upthrust there. So 360 newtons of tension, right? It's the same idea. I just, that's what we call a TE, transfer error. It's a shame when you know all the physics, but you write down the number wrong, okay, and you get the incorrect answer. So like, avoid transfer errors. That's a good sort of lesson learned here from my mistake. Learn from my mistake. Or make your own mistakes and learn from those. That's a good way to. All right, power equals force times velocity. Let's make sure we substitute the correct force. So the output of the motor at that position X is providing this much force, right? 200 from the upthrust, 360 in tension. To move it at a velocity of 0.02. And so that's what we multiply. 360 times 0.02 gives us 7.2 watts of power. And then the question goes on to give us some sort of conceptual questions here. It says, the cylinder is raised with constant velocity from position X to Y. State and explain the variation, if any, of the power output of the motor as the cylinder is raised. Numerical values are not required. This is where we talked about the upthrust force decreases as we lift it up, and therefore the motor, to keep it at a constant velocity, is going to have to provide ever more power, right? Because now it's required to provide all of the force. They're saying numerical values are not required, but we could sort of say, well, this upthrust force is going to decrease from 200 to 0 as we lift it. And so the motor has to provide all the rest of that force. So instead of only providing 360, it's going to have to provide all 560 newtons of force to lift the weight of that cylinder. And so the power output of the motor is going to have to increase, right? To keep it at a constant velocity, it's going to have to provide more power in order to do that. And then lastly, it says the rate of energy output of the motor is less than the rate of increase of gravitational potential energy of the cylinder. So we're increasing the gravitational potential energy of the cylinder, but the rate that the energy output of the motor is less than that. And they're saying we're not violating the law of conservation of energy here. Without calculation, explain how. And you could either say that the oil itself, the upthrust force, is doing work to help lift it, or you could say that there is the oil filling back in the gap left by the cylinder is decreasing its gravitational potential energy at the same rate. Okay, and so there's a net energy balance.